thank you all for coming, and thank you for the invitation. It's great to be here in person and give this talk. So today I'll be telling you about some work. This way. Yeah, it's not quite happy with this. Yeah, well, okay, it works when I press on the laptop. Sorry about that. So I'll be telling you about some work that we recently did at Stanford with all of these wonderful collaborators, which followed up on a paper that I wrote earlier this year about computing the de Sitter entropy in 3 dimensions, the entropy of the cosmic horizon, microscopically as the microcanonical entropy of a dual theory that inhabits the cosmic horizon. So that's the aim. I want to compute the Gibbons-Hawking entropy of the horizon in dS3, along with its leading logarithmic correction, as a microcanonical entropy of some theory that sits on the horizon. And what allows us to do any of this is the so-called TT bar deformation and its relatives, which allow us to describe holography in finite space-time regions. And this was first understood in anti-de Sitter space. So the conventional picture of ADS-CFT is to say that gravitational physics within space of negative curvature, asymptotically anti-de Sitter space, is dual to a conformal field theory that lives on the asymptotic boundary. And what we are able to do with the TT bar deformation is move the boundary inwards to some surface, some time-like surface, that encloses a region of finite volume within ADS3. And the picture one has in mind here is a BTZ black hole, where we can bring in the boundary as a sort of Dirichlet wall all the way to the vicinity of the black hole's horizon. What we mean by this deformation is the following one-parameter family of theories we can define on the space of 2-dimensional quantum field theories that start with an undeformed theory, and for our purposes, this will be a holographic theory with a sparse light spectrum, which admits a large C limit. And what we do is define the following differential equation for the effective action, where at every step of the deformation, we construct the TT bar operator, which is this combination of stress tensor components contracted appropriately, and add it. And note that we're doing this iteratively, which is the subscript, what the subscript mu over there is trying to indicate. When we do this at the fixed point, for the CFT itself, this combination of stress tensor components is literally just a product of the holomorphic and anti-holomorphic parts of the stress tensor, which is why it's called TT bar. But I will maintain this notation to describe the complete covariant object even away from the fixed point. And due to certain properties of this operator that I'll describe, such a deformation is solvable, meaning we can follow certain operators all the way along this flow. In particular, if we look at the expectation value of this operator on the plane or the cylinder, it factorizes into products of one-point functions of the stress tensor. And I said observables broadly, but specifically, the observable of interest to us will be the energy spectrum of the theory on the cylinder. So what we can do here is use the flow equation we defined for the effective action and then extract from it flow equation for each of the energy levels. And using the factorization property I mentioned before that holds in any translation invariant state, namely momentum eigenstates, for instance, and our knowledge of what the various one-point functions of the stress tensor mean, such as energy, pressure, and momentum, we can write the following equation, sort of nonlinear first-order differential equation for each of the energy levels. And what we need is an initial condition, like in the picture I sketched before about what theory we're deforming. When we choose a CFT, we can solve this equation exactly, and we get the following result for the energy spectrum. Note that there are two signs here within the square root, and for our purposes of describing holography in regions of finite volume in ADS space, and later in DS space, we'll pick the negative sign. The positive sign also leads to very interesting physics. In particular, it leads to Hagedorn behavior of the density of states. But the negative sign is what lets us make contact with the quasi-local energy for a Dirichlet wall within ADS. And as, yeah.
Very sorry, I forgot. I mean, we had some talks about TT bar deformations a long time ago, and I think I remember very little about it. So I'm trying to refresh my memory. This is not a local field theory.
Not necessarily, no.
I mean, I would have thought that it cannot possibly be one because of, like, you know, for example, in ADS, in full ADS, you know, signals in the bulk cannot travel faster than they can around the boundary,
Right.
but surely they can be violated here.
Yes, yes.
So the statement is that, I mean, somehow you don't know exactly how to interpret this as a local quantum field theory,
Right.
but you have an energy spectrum.
Right, exactly.
My other question is, I can see how you have sort of control over an interpretation in terms of a moved-in boundary, so long as you stay in the asymptotic region. I'm confused. You know, in a general dynamical random solution in ADS, you were invoking this picture of like flowing all the way to the horizon of a black hole.
Right.
I don't understand how you could have that kind of control. Like, you know, what would you say about that flow if you had two black holes orbiting each other or something, right? If it was like a complicated dynamical solution, like I would have thought that once you leave the asymptotic region, this interpretation somehow breaks down.
Right. So I have two comments about the second point you made there. So what you can show is that some version of this equation is basically the radial component of the bulk Einstein equations. And your ability to describe what's going on at this Dirichlet wall is basically translated to your ability to being able to solve the Einstein equations, both with this condition and the sort of momentum constraint. So you're basically solving a sort of...
When you say radial component of the Einstein equations, you've identified a radial variable. There's a covariant way of doing that if you're in the asymptotic region, there are Pfeffer-Graham coordinates and so on.
Well,
in general, it's not clear what you would mean by that.
Right, so you're basically recovering the Hamiltonian constraint, but now instead of doing it with a Cauchy slice, you're doing it with a sort of radial slice. And for now, we'll keep things Euclidean, so it's basically solving the Einstein equations as a sort of elliptic system with some fixed radius boundary conditions. That's not to say that it's easy to do. And it's not to say that we should have much hope of being able to do so in some general higher dimensional setting where you can have gravitational waves and all these other things. But thanks to the simplicity of three-dimensional gravity, the Pfefferman-Graham expansion essentially truncates. Which means that you can answer this question of what happens when you bring the boundary in however much you like. Basically, you can talk about a Dirichlet wall. You can sort of fill in a Dirichlet wall with an ADS solution, including a BTZ solution, and compute quantities such as quasi-local energies and so on, because the class of solutions is entirely known in a sense. So yeah, that's. Thank you for the question. So here, mu is just the deformation parameter. What it gets associated with in the bulk is the radial direction. It's a sort of radial coordinate, so to speak.
And then in the product slide, what is L? L is like the
Right. So L here is the, so again, now we're purely in field theory. L is basically the radius of this spatial circle. So thank you for those questions. I'll proceed to say that when we deform a conformal field theory, the only thing that matters, it seems, is the dimensionless ratio of the deformation parameter and the square of the radius. And we can recast our entire exercise in terms of this one variable, which simplifies our life immensely. And we'll come back to a cousin of this equation when we discuss de Sitter.
Vasu, isn't L just LHS? Isn't that like a bulk quantity?
No. So here we just imagine that L is, so here we don't quite know what the bulk is yet. So L is just the radius of the cylinder.
Oh, okay, it's the radius of the cylinder.
Yeah, and you see, what it'll be associated with here is going to be this ratio of R and the cutoff radius in G. The deformation parameter itself is going to be related to GR, like, the product. Sorry, LGR, R sub C. In the way we write down this metric, RC is weirdly dimensionless. But anyway, when we translate from boundary to bulk variables, this formula is the same as the formula for quasi-local energy of some configuration that looks like this, which is basically a Dirichlet wall filled in by ADS, some ADS solution, including BTZ solutions. And the radius of this Dirichlet wall is R sub C, the proper radius from within the bulk. And for the purpose of this talk, we will just be looking at these two observables that we're matching between the boundary and the bulk. So we're talking about the energy spectrum on the boundary and the quasi-local energies of various configurations in the bulk. And there's, of course, the open question of how much more we can compute, what other quantities we can tame. We have by no means exhaustively completed this table. But in order to discuss the de Sitter entropy, what we have here will suffice. So in the bulk view of the TT bar flow, which I've expressed in words so far, is the following. We start with an undeformed theory in the space of 2D quantum field theories, and we trigger this deformation, and we follow it. And as we do so, what we're doing is moving radially into the bulk into some truncated ADS space, meaning I go here, I compute the energy spectrum, and I compare with the quasi-local energy. Well, okay, here this would really be the ADM energy. But then as I go further in, I'll be computing quasi-local energies, and I find that they match with the Dirichlet wall at the radius that I described earlier. And this was first proposed, this correspondence was first proposed by Mikko, Meze, and Verlinde in 2016. And the modification to the story now is going to be the following. Perhaps it's conceivable that if we can describe gravitational physics within some finite region of anti-de Sitter space, then maybe some tweaking of the story might let us describe gravitational physics within some finite patch of de Sitter, and in particular, perhaps the observer patch of de Sitter. So depending on the picture you like, we're either talking about some time-like boundary within the static patch, which on global de Sitter looks like one of these vertical gray lines that end at the horizon. But we'll get there. So just to keep in mind what we're doing, we're talking about world tubes. So this is the de Sitter Penrose diagram. The lines over here are not boundaries. They're really just whirl lines of some observer. And we're talking about world tubes that surround such an observer of increasing radius all the way up to the cosmic horizon. So in the limit, which I will describe what that limit is, we can describe the stretched cosmic horizon, essentially, if we're going out this way. And we'll see that there's a possibility also of going this way. And what's interesting is that if we were to periodically identify time, then each of these world tubes are tori. And in particular, the static patch metric in Euclidean signature describes a weird fibration of tori over S3. They sort of cover a hemisphere with tori, where as you approach the horizon, the non-contractible cycle of the torus shrinks. And strictly at the horizon, it pinches, and your torus goes over to being a hemisphere. So normally when one would compute the de Sitter entropy, you imagine computing the action on shell with the boundary conditions on some hemisphere. And this is just to show that you, in principle, can approach the same quantity by looking at these toroidal slices and approaching the horizon this way. Also, the non-contractible cycle is setting the temperature of the dual theory that lives on one of these world tubes. And you see that as we approach the horizon, we're taking the high temperature limit in the dual theory. So this is roughly laying out how it is we're able to compute the density of states and why it has something to do with perhaps the de Sitter entropy. Because in the high temperature limit, the partition function is really just its normalization, which is the density of states. And what we want to show is that's e power a over 4g.
What picks out this correlation that you showed?
Right. So I've told you how to do this post facto, but basically, if we were to solve the radial Einstein equations, the sort of radial constraint equations with this cylinder topology of the slices, then this is the patch we can cover. That's one way to answer the question. Alternatively,
I'm asking about the patch. The patch is covariantly defined as being.
Right.
Well, you still have to pick a world line first, but then it's defined as the path in the future of that world line intersected.
Right.
I'm asking about the foliation, because if you're not
Right.
exactly in the Sitter space, but in some perturbation there are, I mean, if you added matter to this.
Yeah. Oh, it's a good question. So basically, what I can say with confidence is that if I compute the, say, the partition function of the appropriately defined deformed theory on the torus, alternatively its energy spectrum, then I'll find a match with the quasi-local energy that I compute with this slicing. And similarly, in the quotients of this space, which are the point particle states in de Sitter, in dS3, basically. And you're right that, well, the horizon, and this becomes tall de Sitter space if I have, say, point particles. But in that case, too, I'll basically be computing the energy of certain excited states. And I can, again, look at the quasi-local energy for one of these slices, and they match. So that would be how I say that we know that this is the same slicing.
But in general, the symmetry will be broken, right?
Right.
So just
ideally, this TT deformation provides case fixing of the radial coordinate, but
Right.
you know, technically you can do only dS3, but probably you're generalizing more, which may not be even possible. People don't know. But if it's possible, then this new parameter can be used as a radial coordinate. Then that's the case fixing procedure, specific one, holographically polygonal, and that's it.
I mean, you need something like Pfeffer membrane, right? You need a universal form of the metric
You don't need a
that is always applicable, because otherwise, how do you decide which coordinate it's supposed to represent?
Yeah.
And
Well,
in a case of very symmetric system, you probably can guess that's just radial coordinate in general, no. But you can still claim that, of course, by checking that everything is as predicted by Einstein equation, and it's a specific features.
Okay, I hope that's true. I mean, it's the existence of feather invariant coordinates was a very non-trivial mathematical fact that it played a central role in the ABS-CFT dictionary. Right?
yeah.
I mean, the fact that I could write symmetric near infinity in a certain way with the stress tensor of the CFT and there is a symmetric perturbation, all of that relies on that, and it's valid near infinity because there happens to exist this universal coordinate system.
That's exactly what I meant, that whether nobody knows whether you can do something like that in general space.
Right. So if it helps, Raphael, basically the equation that the set of equations that I'll be solving is equivalent to the set of constraint equations. And in general, what that buys you is some thickening of your initial data surface, like in some general setting. All you can really say is that, I can probably propagate this data forward by some amount. And then, of course, you gauge fix to say that something is the radial coordinate, right? You gauge fix the Hamiltonian constraint to say that. But of course, you could have chosen another gauge fixing parameter. But the only guarantee you have is for that neighborhood. And in nice settings, like in 3D gravity, you can actually push it pretty far. But in general, I agree that it isn't known, or we don't have guarantees that we'll be able to describe such regions. So, well, thank you for the discussion. Okay, so the modification on the field theory side that will enable us to describe physics in de Sitter space is an addition to the TT bar story, and sorry for the notation here, this should be mu and not lambda, where we add something proportional to the boundary cosmological constant to this flow equation. So instead of just deforming with the TT bar operator, we're also deforming by the boundary cosmological constant. And in order to do this, we need an initial condition that doesn't start at the 0 value of the deformation parameter, because that's a singular limit. But we have to use the TT bar deformed CFT itself as initial conditions for such an equation. And now, depending on where you do the matching of the trajectories that you get by looking at this deformation and the TT bar deformation, you fill in the picture that I showed here in the bulk in different ways. Before going there, much like we did before, we can introduce dimensionless variables and solve this equation. And what I'll do is just keep this eta parameter general, where if we have eta equals 1, we're describing cutoff ADS. And if we're describing eta equals minus 1, we're describing some cutoff patch of ds. And so basically, this is an equation for the energy levels that has a general solution. And in order to fix the integration constant, we will have to choose initial conditions. And these initial conditions will come from the TT bar deformation of the CFT, which in turn describes some finite region within ADS. And so what I'm alluding to is that we have to look for configurations in spaces of negative cosmological constant, which look indistinguishable, at least locally, from some configuration in a space of positive cosmological constant, so that we can do this matching. Now, there are two options that we explored in our work. There was an original prescription due to Gorbenko, Silverstein, and Toroba, where what they did was they said, near a whirl line, thanks to the equivalence principle, you can't really tell which spacetime you're in. So run the TT bar flow to some very large value of the deformation parameter and use that as initial conditions for this TT bar plus lambda 2 flow. And what that lets you do is fill up this patch, the static patch, with slices of increasing volume starting from the whirl line itself. And that's what we call the pole patch, or the PODE patch, which is in Lenny's terminology. Alternatively, we can look at the near horizon region for a BTZ black hole of horizon radius of 1 ADS length. And the near horizon region is indistinguishable from that of the de Sitter static patch in vacuum. And this provides another point at which we can join these two flows. And this is what we call the cosmic horizon patch. And here we fill out this picture in the complementary direction. And there's subtle differences in the energy formulae. But having this in mind will certainly give us more insight into the entropy calculation. And basically, we'll be able to use our knowledge of the density of states of a holographic theory with a sparse light spectrum to obtain the entropy of the de Sitter horizon. And so basically, it's the microstates of the black hole that are counting whose count provides the entropy of the cosmic horizon. And that's the sort of weird answer that I want to try to motivate here.
Is the equation of the T bar plus lambda
yes.
the other way around in the two things?
Well, yes. So, right. So that has to do with the sign of the extrinsic curvature, basically. So the first derivative of the metric along the radial direction. And that in particular is sensitive to the part of the quasi-local energy that doesn't involve this one, because the extrinsic curvature is related to the Brown-York stress tensor, and the Brown-York tensor has a counter term subtracted, and that counter term is this one. So if we ignore that, you see that there's a difference in sign here, and this is basically the difference in the sign of the extrinsic curvature, depending on whether you're going in one way or the other.
Oh, so in terms of kind of parameter of evolution, it looks like going to the same direction. It's just
yeah, exactly.
It's
yeah.
included in this sign change.
Yeah, yeah. Thank you. So in this original pole patch, we have the following entropy formula, which when you take mu over L squared to be very large, looks identical to the energy formula you would get in the ADS case, the cutoff ADS case. So that's how you fix the initial condition that lets you fix the integration constant over here. And in the cosmic horizon patch, what we do is actually fix the initial condition at a different point, and namely, like in the bulk, that corresponds to the vicinity of the horizon. But the vicinity of the cosmic horizon looks a lot like the vicinity of the BTZ horizon with R equals L, which, one can check explicitly. And in many ways, what we're doing is giving some justification to the hint provided by the fact that A over 4G for the BTZ black hole is the same as A over 4G for the cosmic horizon. But yeah. Now,
It's not right to argue that these look same. You're already using that entropy.
Exactly. Yeah. I mean, in some sense, the answer was already there. But the question is, what why in field theory should that be manifest? And now, one thing I didn't mention is that with the negative sign that we chose within the square root, we really do have to truncate the resulting spectrum in order to maintain unitarity. Otherwise, the energy levels go complex. Having to do so to describe the physics of the observer patch in de Sitter space is good, because that in turn tells us why the de Sitter entropy is finite. But now if we talk about excited states, which are the states when we translate into field theory terms with delta less than C over 6, these are basically particle states. So dS3 has no black hole solutions, but it has point particle solutions, which are quotients of dS3. And the effect of these particles is to sort of make de Sitter taller. And so the horizon is not in the same location as it is in the vacuum. And so if we're truncating this flow all the way up to the horizon of the vacuum, obviously we're going to be missing some patch of these kinds of states. And what we really need to do is have a domain wall with some region of negative lambda and some region of positive lambda. And at the level of analysis that we're doing, we can only really account for the energy of such configurations. But to actually talk about the dynamics of this domain wall, we have to add certain double trace deformations in addition to TT bar, which describe the matter that supports it. Basically, this is going to be model dependent. And however, these are subleading in the entropy calculation. They're order 1 compared to the order C stuff that we're interested in. Now, we can ask whether there's some relation between these two patches.
So you said you can do this, or there's some issue, but you don't care because it's
we can do this, but we haven't. And it's also true that these are subleading with respect to the microstate count for the entropy. So it's not urgent for us to actually have to answer
that I understand.
Yeah.
But the point is that that's why you just simply don't care.
Yeah.
Or you can, or there's some problem which you already know.
Well, I wouldn't say it's a problem. It's just, I mean, to the extent to which there's a problem, we know what the solution is, and we can discuss that later if you want. So we find that actually these two patches have an interesting relation. So there's a Hawking-Page-like transition between these two kinds of finite patches within ds, so these two kinds of flows. In particular, when the temperature, which is set by the radius of the non-contractible cycle we get from periodically identifying time in one of these world cubes, is less than the radius of this world cube, this flow is preferred, so to speak. However, when beta and L are comparable, there's a crossover. And what we find is that this crossover is very analogous to what happens between thermal ADS and BTZ in the case of a negative cosmological constant.
Does this correspond to de Sitter? I think I'm a little lost. Which of these things is the de Sitter temperature?
So neither of these is the de Sitter temperature. So this beta is the temperature associated with of the boundary theory that we get by identifying time. So these world tubes are tori. And beta shrinks as we approach the cosmic horizon. So the...
Would there be some relation between de Sitter space of definite temperature?
Right. But the temperature of de Sitter space is... well, it doesn't vary with beta here. I don't think, right? It's...
What is L?
L is the radius of this world tube. So in much the same way as, well, okay, so another way to put it is that if we talk purely in terms of the modulus of the torus that we get by identifying time periodically, then what we're asking is whether or not it's bigger or smaller than 1.
I'm confused because I would have thought that there's a definite temperature that you want to choose for the periodic identification, which is the one of the de Sitter space you're discussing.
Well, right. So let me go back a few slides and show you. Basically, what we want to do is identify tau sub e here periodically and sort of keep this in the definition of the temperature. So we have this warp factor that tells you tells you how far you are in here. And so.
In these coordinates, the temperature, beta should be something like L or 2 pi L, right?
Yeah, in these coordinates. Sorry, so R here is like L in the later slide, but
the curly L is your de Sitter
yes,
radius.
curly L. Yeah, so we want 2 pi L, basically, we wanted to have period 2 pi L. And so...
Is there nothing in the structure of this approach that fixes that from the start?
No, because we're not trying to recover the de Sitter entropy from the canonical ensemble where, I'm trying to say that I have TS, and then T is something I know, and therefore S is A over 4G. Instead, what we're trying to do here is get the de Sitter entropy as the microcanonical entropy in the high temperature limit of this dual theory. So as I take the high temperature limit, the partition function is really just the normalization, and so it's just going to be e power s as beta goes to 0. So yeah.
Okay, don't you want at the end to reproduce the Sitter entropy?
Right, and we will. So we will reproduce the de Sitter entropy as the logarithm of the density of space that we get by.
No, but you have still the thermodynamic interpretation. Theta, which is 1 over 2 pi, and T, which is 1 over 2 pi.
No, that doesn't matter because you can take the Hubble radius to be unit of energy. It's the same as ADS-50. Everything measured in terms of ADS radius. Everything measured in terms of Hubble parameter. The temperature doesn't make sense. Only thing that makes sense is the de Sitter entropy. That's the ratio of Hubble parameter and the Newton constant. So
I don't understand that, Yasunori, because I mean, it doesn't matter if you set curly L to 1 or not. There's still, either, if you set it to 1, then the temperature or the beta you need is 2 pi. But there's still a definite beta that makes it geometry regular in the Euclidean sector. Right? That's not a question of units. It's just a question of not having a conical deficit.
no, because you can take a unit of energy to be arbitrary. Only thing it makes sense is a ratio of dimension full quantity. Entropy makes sense because it's a ratio of de Sitter radius divided by Planck radius or Planck length. That's of course a well-defined thing. But usually
The relevant ratio here is that between the radius and the circumference of the circle. It has nothing to do with units. That has to be 2 pi if there's not a conical singularity.
or the boundary radius.
Yeah.
Oh yeah.
In the just Euclidean time, it has to be identified with period 2 pi units where the de Sitter radius is 1.
Yeah.
Well, so if you went from the microcanonical to the canonical ensemble, then, well, so basically you would find what beta is in terms of, given S as the de Sitter entropy, and given the partition function, you should be able to tell what beta is, and you would recover, not for this ensemble, but a slightly different one that you get the de Sitter entropy. It's just that this is not the.
But in the thermodynamic limit, it shouldn't matter, right? So do you end up getting the?
Right. So where you can make contact is in the what would look like the high temperature limit of this slicing, because only then can you actually cover the hemisphere. And what you do normally is you try to compute the gravitational action on sort of the hemisphere and then interpret that as e power Ts. And then you get the temperature to be 1 over 2 pi L. And so for us to be able to get there, we actually have to run the flow all the way here. And yes, all the way to the horizon. That's when you're covering the entire hemisphere. Otherwise, what we're talking about are two different configurations. Right? So when this temperature is not 0, we're talking about some slice, some piece of ds which you don't expect, to have the same entropy. So in that sense, beta is kind of this beta is kind of auxiliary, if you would like, because you really need to take it to 0 in order to actually make contact with the covariant calculation that you have in mind in Euclidean, the covariant Euclidean calculation that you have in mind. So I hope that answers your question for now. But we can come back to it. So I'll just go through what the calculation is. So
it's still that the Hubble radius you can take as a unit.
I agree. So
and the ratio of the size of the Hubble patch over temperature or something is
right. But what I'm saying is that here, if we keep beta to be something that's non-zero, then we're not even really covering the entire Hubble patch. Right? We're sort of covering we're looking at some configuration where there's just some finite Dirichlet wall within, surrounding an observer. And we don't expect that this configuration should have the same thermodynamic properties as the entire,
So that's why you set the beta equals 0. And
right.
in that sense, you lose one one parameter.
Right,
So
right.
Hubble radius is just a unit.
Right,
but
right.
Entropy still makes sense because entropy is a ratio of the
Right.
of
Correct.
that and then
G, Planck,
G
yeah.
Newton.
Yeah.
And that's of course separate charge.
Right, right. Exactly.
Yeah, okay.
Thank you for the discussion.
So in this crossover, do you mean the region of space-time changes?
Right, so let me make that more concrete. So say we just try to, so if I was computing the partition function of the dual theory on one of these slices, question is, should I fill in this way or this way? Like when I compute the dual action on shell, should I look at the configuration where I'm filling in this way or when I'm filling in this way, right? So that's the sort of crossover that we're talking about. So it still has to do with these weird little patches of the static patch, so not the entire static patch. But basically, when beta is comparable to L, there's a crossover between filling in this way versus filling in this way. So there's some. Anyway, once beta is smaller than L, you basically have the S transformation of your ground state energy, the modular S transformation of it, where beta and L have been swapped. And what you find is that this quantity can be rewritten as the Cardy formula entropy for the C/6 state minus the direct channel energy of the C/6 state. This is a little bit of arithmetic having to do with the funny function that we have here. But one can check that when we take, so basically we take this formula where y0 is c over 3 pi squared. And what we compare is the vacuum when y is taken to 1 over y versus the excited state where y is what it is, but delta is c/6. And the claim is that the S transformed Boltzmann factor here for the vacuum is the same as the direct channel energy for an excited state minus the Cardy formula for the C/6 level. Now this delta equals C/6 level is nothing but the R equals L black hole in ADS, right? That has entropy A over 4G with R equals L, so it's pi L over 2G. And as we take beta to 0, we recover e power s as the partition function, and we get pi c over 3, which is a over 4g, and a is 2 pi l, and c is 3l over 2g. Sorry, I should have maybe mentioned that. So this is what I mean when I say that we only really recover the de Sitter entropy when we actually go all the way to the horizon. And that's when we lose this scale beta. And for this entire configuration, the entire static patch, we can then ask, okay, if I was to interpret this in the canonical ensemble, what would the temperature be? I would recover the de Sitter temperature. And this would be the entropy associated to it. So this is the leading answer. And so, okay, in terms of field theory, what have we done? In the bulk, it looks like we've just said A equals 4G and R equals L. Oh, great. But the reason why any of this is possible is that we have an integrable flow, which means that there are no level crossings. Now, if your original theory was integrable, then for the integrability to be preserved, it's important that we have this property. And I've sort of schematically plotted what happens as we do this deformation, starting with the TT bar deformation up to a certain point, and then the TT bar plus lambda 2 deformation. Although you see that the energy levels are sort of going from here all the way here, none of them are going to cross. And in particular, the spectrum that we're interested in has this schematic structure. We have a sparse light spectrum, so we have some sparse set of states here that are model dependent and non-universal as such, that have scaling dimensions of order 1. And then there's a gap all the way up to this level delta equals C over 6, or energy equals C over 12, where the states are arranged such that the density of states is given by the Cardy formula. Now, this is characteristic of a holographic theory, where the Cardy formula always holds for a CFD, a unitary CFD, in the asymptotic regime where we take very high energies. What's special about holographic theory is that the regime of validity of the Cardy formula is extended. And it's extended all the way down to this particular level, this Hawking-Page level. And technically, what we have to do to obtain the density of states is look at a sort of order 1 band of states around the C over 6. Sorry, I should have moved this in the middle here. But there's an order 1 band of states around the C over 6 level, which actually captures the entropy when we do the inverse Laplace transformation. So this is how, so this picture combined with this one, where this is the spectrum now of quasi-local energies that you have in the de Sitter, in the DS theory, is how the entropy of the BTZ black hole, whose microstate count is described by ADS CFT, now counts the entropy of the cosmic horizon in dS3. And as such, we can basically infer, so this is just in equations what I described in words. So the density of states is really the same. All we're really doing is expressing the original undeformed energies in terms of the deformed energies. And as such, the leading logarithmic correction to the Cardy density of states goes along for the ride. And one can show that this is true by explicitly doing the inverse Laplace transformation in the deformed theory, or you can derive a differential equation that lets you actually, that you can solve to see that this is a solution to the desired order of accuracy. And we find that in addition to the leading log correction, we get this 3 log A over 4G term as well. And now the takeaway in higher dimensions, so what would one what might one expect? So sort of what has this taught us, this exercise? It's basically said that we should anticipate that some higher dimensional generalization of this story can allow us to describe the microstates of the de Sitter ground state in terms of the microstates of an ADS black hole with R horizon equals LADS. Now, there are additional complications or features of higher dimensional de Sitter space, such as black hole solutions and things like the Nari geometry, all of which have very interesting features that we need to understand better. But we're fairly confident that for the ground state, something like this should hold. So in other words, we're fairly confident that the microstates of the cosmic horizon of empty de Sitter space are those of the appropriately defined ADS black hole that are flowed down through these irrelevant operator deformations. And in higher dimensions, we only really have control over such deformations for theories, large N theories that have holographic duals. So generally, we probably can't define this and solve these equations as we'd like, but for this narrow class of theories, there is some hope, and that's future work. Thank you all for your attention.
Since you have a little time, any more questions for Council?
Do you have a specific expression for higher dimensional deformation?
Yes. I'll use this. Can you see?
Yeah, you can also go out if you need more space or something.
Yeah, sure. I mean, this should suffice. So I wrote it as t squared, but I'll put this in quotes. What it actually means is basically something like this. Now, there are a number of issues with trying to make sense of this in general quantum field theory in higher dimensions. So in 2 dimensions, you can define this operator as the coincidence limit of, at least the expectation value of this operator is a coincidence limit of a contracted 2-point function of stress tensors. And you can use the fact that the OPE of stress tensors is closed within the identity module to prove that there's a local operator that exists called TT bar. In higher dimensions, we have no such guarantees. I mean, the TT OPE generates whatever you like, all kinds of things. So where you have some hope of making sense of this is in some large N theory where double trace stress tensors will factorize into expectation values of single trace ones. So in some sense, we should call it the expectation value of T squared operator. And that's what I meant when I said that you can kind of make sense of it.
In that sense, like this one of the equation or something, no hope.
Unlikely, but...
And leading order pretty much is zero for your matching.
Right.
So it is not the calculation of log T's would not.
Yeah. Right. I mean, also the thing is that it's only through our knowledge of the Hawking-Page transition in higher dimensions that we have an expression for the density of states of holographic theory. Otherwise, it's not like we have something like the Cardi formula readily available.
So this property of flow and so on won't persist at the high order, right?
Right. Yeah, it won't. We don't know. I mean, yeah. Also, I mean, integrable theories don't exist in higher dimensions, and so you don't really expect that there are deformations that would preserve integrability and so on. So.
Any more questions? Not, let's finish Vasudev.